Today we've got a real treat, sort of, maybe. Zero knowledge proofs. They're probably the scariest thing. I already feel like I have zero knowledge in so many cases, but now we have a product that apparently is so simple and easy to understand. It requires zero knowledge, but when you look at it and see the words, I don't even know how to pronounce this, affini, I'm like, if this requires zero knowledge. Groth, the heck? Why is it 16? Who knows? Zero knowledge proofs are terrifying because I'm dumb and they are not. And anyone who has ever talked about them to me assumes a high level of intelligence on my part, and that necessarily means that I get lost roughly within about Groth 16 seconds. So I was very concerned, but I knew at some point in my life I was going to need to try. Thankfully, though, smarter people invented this wonderful technology called artificial intelligence, which is now the only kind of intelligence that I have. And so I've been able to start trying to use zero knowledge proofs. Now, why in the world did I start now? Well, you've heard me speak a couple of times about this game wager pool contract that I'm building, which I'm very excited about. And for those, the uninitiated, I'll remind everyone what it is. I'm taking the Blend protocol, the SwapSwap protocol. There's a fee vault protocol or contract that the Script3 guys who built Blend have written, which essentially allows, the fee vault essentially allows a bunch of users to deposit through this fee vault contract into the Blend protocol, and then all of the yield that gets generated on those user deposits gets paid back into either the users or, in my case, the admin of the fee vault, which I can then use to distribute however I want inside of my contract. So I'm building a game contract which will distribute the yield from the deposits into this fee vault, deposit that yield to game players. So there's 3 right now factions. So users will players will elect themselves into one of these 3 factions. They will play games. As they win games, they win points for their faction. At the end of every day, the winning faction is allowed to claim the yield that's been earned for that day. I've been working on this contract for, let's be honest, AI has been working on this contract for a while. Pretty happy with it. It could be filled with bugs. The main safety mechanic, though, is that it's relying on Blend, it's relying on the fee vault, it's relying on SwapSwap, which are all audited contracts. I'm just kind of writing a contract to tie those things together. It's an upgradable contract, so when things break or, hey, I didn't get my yield, or someone was able to gamify the system, at the very least, because it's zero loss, you never lose your underlying deposit. You can always get your deposit back out. The only thing that's lost is the yield if someone cheats or finds a vulnerability, which we can then just patch. So it's this kind of cool way to build up this experimental game money to distribute to game players. Pretty happy with the contract, about ready to deploy it. I've deployed it, and now it's game time, baby, which then necessarily begs the question, how am I supposed to build a game that lets people win money that isn't inherently hackable, that actually has some level of fairness, verifiable fairness, that the players can't cheat, the server that hosts the game can't cheat, that essentially nobody has to be trusted, that there's some way to encode game rules or game logic, and then from that verified game rule component, everybody has to play according to the rules. It produces some proof at the end of the day, which we can then use to pick the winner, verify the winner, so that game can close. The winner can take their faction points, push it to their faction, and move on with other games. So that's the whatever the happy version of the hellscape is, but still kind of confusing and difficult. That's where I am right now. That's where the zero knowledge proof comes in, because this is exactly what zero knowledge proofs aim to solve for, is this idea of let's prove that. Like, zero knowledge proofs can do a couple of different things in like obfuscation or secrecy, but still have verification. But in my case, we can't trust anybody in this system, and so we have to somehow create verification that game rules are being followed, irrespective of the server or the clients that are running this game and contributing moves, et cetera, et cetera. So that's the realm I'm kind of operating under. It's a long journey because I don't understand zero knowledge proofs, and still don't, though I have learned a lot about them thanks to AI. There's one Sorbonne example, well, maybe there's two, but there's one Sorbonne example that's worth calling out here that I'm kind of operating under. We have one zero knowledge prover or verifier right now, cryptographic, and this is this BLS 12381, which is kind of easy to remember because it's 123, and then just all you really have to remember is 81. But there's a dash in there. It's kind of like your social security number, and you're like, I don't actually know what order these numbers, and there's spaces, but I'm not sure where. The curve is this. If we go to one of these proofs, I think it's included here. The protocol is, in our case, is Groth 16, but the curve is the important part, and that's that BLS 12381. There are other more popular, in Ethereum, they have the, BN256 or something like that, which actually is quite difficult in the AI realm, where most of the time when you start asking AI to do zero knowledge stuff, it's going to use the wrong curve. So you have to pretty explicitly keep telling it, stop it, and use BLS 12381. Rumor has it that maybe in Protocol 24, we will actually get BN256, which will be awesome. Or is it 254? I don't remember. We'll get one of the curves from Ethereum, which will hopefully help AI to actually produce proofs that are a little bit easier to work with the code to get those proofs. But I'm getting ahead of myself, right? What is a proof? What are we doing here? Well, we have this example here, which is actually super helpful, this Groth 16 verifier, which I'm going to paste in the chat. 254, not 256. Don't get it confused. It's SHA 256. It is BLS BN 254. Cryptography, man. Okay, so I just pasted the link to that example, the Groth 16 verifier, and you'll notice like the code for it is very minimal. There's not a lot going on, but it's also very few comments, and the comments that it has are things like this piece of garbage. So it's not super helpful, other than you start to have some information about what kind of arguments are going to need to be provided for you to actually be able to pass in some sort of verification key and proof, as well as public signals. So you've got some idea of what you actually are going to need to pass in to be able to prove anything, but then also there's a test, which is really helpful for crafting, particularly from strings, from these different proof files, to actually be able to craft the arguments necessary to go and actually do this verify proof. You're going to have to craft a proof, craft this verification key, and craft the output. But that's also really, really helpful to know. For me to do a zero knowledge something, I'm going to need whatever VK is, whatever proof is, and whatever output is. And I'm just kind of walking you through the most useless explanation of zero knowledge proofs that at the end of the day is all you really need to know if you're going to actually make use of these things. And there are some high-level concepts that I'll touch on that will help if you too want to go along this path of building games that we could then accept into this. I'm not exactly sure what I'm going to call it. The working name has been Blend Together, so I might keep working on it. The contract that I built for giving out game rewards from the Fee Vault, so we'll just keep calling it Blend Together for now. But if you want to build games that are then on the Blend Together protocol, this will all be helpful information to ensure that you're building games that are actually provably unhackable. To some extent, or at least, best effort type of thing. Okay, so there's a test. there's the library file, and that's all there is to it. Everything else is the cryptography that you don't really have to worry about. There's a data file, which is very, very helpful, both in giving some clues in the auxiliary directory of what's actually being proven. We'll get to that in a moment. But then also the proof file, the public file, and the verification key. So the clue here is that for you to do cryptographic stuff, you're going to need a proof, a verification key, and this public JSON. Not even public JSON. It's just the things that the prover spat out at the end of the day, what it's actually trying to prove. So in my case, instead of something like 33, I would be proving, did player 1 win or did player 2 win? Okay. But how do we actually get to that point? Well, the auxiliary file helps us a lot, where essentially you're trying to come up with a collection of rules, or a rules file, a rules program that says whatever game we're trying to craft, we have to come up with some set of rules so that when players are playing, we can verify that they're playing by the rules. And this is where you're going to spend most of your time, is actually deeply thinking about whatever it is game that you're crafting and ensuring that rules are followed. And I picked a fun, easy, simple game, Pong, and I had no idea how actually almost impossible it is to actually verify the rules of Pong, because the rules of Pong are really simple. Score on your opponent and win a point. But to verify that the deeper rules are being followed, you have to be the paddle can only move at a certain speed, which requires both velocity information and time information, so that the paddle doesn't blink across the screen when you're not looking, sort of a thing. It's you can't assume that it's going to be played on a graphical interface. The bounces of the ball, when it bounces, is it following physics logic, or is it floating around? And that's another factor of time. And I guess it's not really time, because time is a concept of really just of ticks of moving forward. We might call them frame rates in games. So are we going to have to verify each individual frame, or can we assume based off of trajectory, size of the box, that once it hits a wall, it's going to move in this direction, so that if it interacts with a paddle, it will hit it at a certain direction at a certain velocity? It starts to get you're dealing with some pretty interesting physics components that then have to be put into this CIRCOM, if you're working with CIRCOM. But the CIRCOM is basically taking the in my case the physics, but it's building the rules engine. This is what is going to generate the proof that as inputs come in, it will verify that those the flow of whatever the game is, or the rules are being followed, so the proof at the end of the day can guarantee the rules were followed. So it gets quite dicey in my case, even with something as simple as Pong, to absolutely guarantee that both players and the server. I don't trust. What I really want to be able to do is build a binary that I could pass to anybody, and they could run it on their own server. That would then open up. There's another problem with Pong. If I want to be able to play me versus Elliot, we're not going to both be on the same computer. So now somehow we've got to be able to communicate about this game of Pong that we're playing in real time. So in my case, I would use a WebSocket server. You could use RTC probably, and that maybe would be okay. But I want to have a single central server that can then run the prover, produce the proofs, verify on chain, those types of things. You could probably do WebRTC between just two computers, and maybe I'll build a version of that where that's the case. But it gets a little dicey, because web, the only complex stuff you could do now has to be handled in WebAssembly when you're running things like Rust or some of these heavy cryptographic primitives. So it's nice to have a server that can run Go or Rust or some of these more native languages for running cryptography. So, okay, we'll assume we have me as player 1, Elliot as player 2, and the server as the kind of producer, the runner of the circuit, the creator of the proof, and also just running communication between Elliot and myself. through a WebSocket server. Well, what's that WebSocket server communicating? Well, it's communicating, I'm ready to play a game, and then Elliot says he's ready to play a game. It coordinates and says there's 2 players ready to play a game. Well, I don't want the game to immediately start because maybe I've been waiting for a while and I turned it off or wasn't looking, and eventually I go back, oh, Elliot's ready to play. So now there's a verification. We're both ready to play the game. Boom, the game starts. WebSockets are communicating that the game started. But I don't trust the server, right? So a couple of the versions that I was building originally where the server kind of ran the logic of where the ball was. Well, that's problematic for a couple of reasons, with it trying to communicate to at least 2 computers, who knows how many games of Pong it's playing. The frame rate would be pretty low if it's trying to communicate, where the ball is every single tick. So it'd actually be way better if both players were running a version of the game, just like traditional games, where you actually download the game and the physics all run locally, and then it just communicates events, when I shot my gun, when I moved my paddle, I guess, in Pong. So the only events that are being communicated now with the server, with both of these computers running their own version of the game engine, are when the paddles move. Those are the only things you can do in Pong, is move the paddle. But now we've got a problem that, let's say the ball is like right on the edge and I'm in the process of moving my paddle. There could be a slight latency on when Elliot's computer, which is running in real time, renders it hit the paddle, and where I may be 1 or 2 ticks, frames behind where Elliot's paddle was. And so the velocity and direction of the ball is different between our 2 machines, which is going to change the whole physics of where it's going to go next. And so you have to say, okay, whoever's paddle was closer to the ball, they're the one that ultimately decide how they hit the ball. They still need to follow the rules, right? They can't just jump, and they can't make the velocity be absolutely insane. It has to follow the rules of whatever's reasonable at where the paddle was, ticks behind where the paddle is now, and where it hit the ball and its direction then. But they ultimately make the decision, and then they communicate that decision back to the other player, which may have a different perception of where the paddle was, but can then make a correction very quickly on that tick or in a very close near tick to say, okay, we thought the paddle was here. Turns out it was a few ticks ahead because we were maybe a few ticks behind. So we'll correct the trajectory of the ball to what the trajectory is that Elliot perceived. And so long as it's still following all the rules engines, now we're all good. Those things can begin to communicate again. And the physics just make things so much more difficult to actually create any sort of prover. Because ultimately, I also don't trust the server not to have like a bias towards one of the players. To also say like, okay, you sent this signal to me via your WebSocket, but I'm not going to believe it, or I'm going to modify it in some way. So now you've got to have the server, when it receives events, they can't be trusted to not modify them. You can't trust the users to have sent you accurate information, like it has to be following the physics rules. So those actually need to be signed, so that there's proof that the user actually submitted those changes, and like I'm not making pushes to the server from the client about what the other player is doing. So there has to be like this authentication or signing of events so that the server can ensure that they're official moves from either player. But we're also not trusting the server itself to not lie about the state of the game, which is why those moves need to be signed to ensure to the verification model, this CIRCOM circuit, that I'm only interpreting signed events. I have to have a signed event that's coming in from the players so that the server itself can't modify the inbound events. And regardless of the game that you're building, these things all have to be true, that you don't trust either any player and you don't trust any server. And at the end of the day, the only thing that we're absolutely sure is the rules engine itself is correct, understands the rules, knows what rules are important, and is ensuring that any values coming in are guaranteed to be accurate or approved or signed by whatever user is submitting them. Okay, but why is that important? Well, inside of this CIRCOM, let's take I did an example here think it was this one. This one's really basic, right? It's just saying I want to multiply two numbers together and get the result. And the prover is not going to know what the inputs were. The inputs kind of get baked in, not the specific inputs, but the idea that we're going to have this C and this A, or I'm sorry, this A and this B, we're going to multiply them together. You don't need to have hard-coded what the values are, just like you don't need to have hard-coded into the Pong game what the values are. You just need to say, when you receive values, this value is a ball velocity, this value is a point, this value is a wall bounce, et cetera, et cetera. And then when those values change, you're just verifying that when I get values, I'm measuring them, in my case, against some sort of physics engine where I say if a paddle moves, that's valid, but only if its previous position and its new position are within bounds. If the ball bounces and it has this velocity in this direction, when it intercepts with a paddle, do the physics check out, or has the velocity or the direction changed from when it hit the wall last? And when you kind of get to understanding Pong, there's really only a few things that you need, and that's how big is the box, how big is the ball, how big are the paddles, and where are they in position. Like the physics actually become a lot easier because as soon as a ball interacts, particularly with a paddle, you can already predict, okay, if it's moving in this direction and at this velocity, and even the velocity doesn't matter that much unless you have the concept of time or ticks. You know that once it interacts with the bounds of the walls, you know where it's going to land. And either the paddle's there or it's not. The paddle could get there or it couldn't. And when the paddle's there, then you can start to decide, okay, well, now it interacted with the paddle. It was allowed to because it could have reached there under the laws of physics. But after that directional change, we know where it's going next, and immediately can know exactly where the paddle is going to have to be on the other player's side. So you're interacting or thinking through all the game rules and stuff. But in our case, like just with this basic multiplier, the rules are very simple. There's no bounds other than like, I don't know exactly, to be honest, what these, if they're U32s or 64s. I guess I've got this rules engine right inside of the auxiliary file here. The circom here. What these actual values are doesn't look like it says. But it's just going to take those two values and multiply them together. You could put other constraints that would say things like the value has to be below a certain number, or they can't be equal to each other. I mean, you could put any rules you wanted, with the idea just being that in this case we've got two values, two inputs, A and B. When we multiply those things together, there's, I guess, one other really critically important piece of information. After you build a circuit or the prover, the rules engine, you generate a verification key. And that verification key is critically important because it's tied to this circuit itself. And this verification key is technically, in our case, we include the verification key as an argument to the contract, but you would actually hard code the pieces of this verification key to the contract itself, to what's being verified, because that's what proves when you're actually like the verification key and the circuit are tied directly together. They're linked. Only that verification key is valid for that circuit rules engine. So when I give you a verification key and then you generate a proof, I am absolutely sure that if the proof's coming out as true, or I guess false, but the proof will only be valid if you used my verification key for that particular circuit. So it's a little bit like asymmetric cryptography, where like if you've signed for something and all I know was your public key, I know that you know the secret key if you're able to produce a signature for that public key. So you can pass around the verification key and say, everybody can have my verification key to make proofs, but the only way that proof will be valid is if you were using my actual circuit, my actual rules engine that generated the verification key. So it's like, instead of asymmetric cryptography just being like a public and private key, it's a program and a public key, a program and a verification key, which is really, 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 really cool. Because now you can create like a program that essentially you can hand off to everybody and say, if you run this program, I have a guarantee that so long as the verification key matches with that program, that you ran my actual rules engine. You had to follow my rules. Now, hopefully I made my rules correct and there wasn't some caveat. in the rules that I generated, but I can have the guarantee that you followed my rules. And within those rules, then you're able to then obfuscate. In my particular case, when a proof is made, the arguments themselves are hard-coded into the proof. So what's produced at the end of the day is this proof file that doesn't include any inputs. So when I go to grab this proof and then see if you actually followed my rules, I have no idea. I have no knowledge. I have zero knowledge over what the actual inputs were. I just know that this was the output, and at the end of the day, it's 33. I don't know how you got to 33. I don't need to know how you got to 33, because what was coded in is simply the fact that you followed the rules. So you took an input, you multiplied them together, and reached 33. Maybe there's multiple ways to get to 33 with the inputs. I don't know, and I don't care, so long as you followed my rules and these two values were multiplied. So I can then take this proof, go and prove it on the blockchain, which is going to look at the verification key, and it's going to look at the proof, and it's going to look at the outcome and make sure that the outcome matches. So it doesn't like rerun the program. It doesn't rerun. It just looks to see if the verification key matches with this particular proof. It doesn't go, you don't have to provide the inputs somewhere else. The inputs are encoded intrinsically into, encrypted, intrinsically into the proof itself. So if I go and I verify this on testnet, it should come back as true. It actually executes this on chain, so that is valid true. If I change the output and I say I actually think it's 32 because I want to cheat and say that this is the value, give me $100 or whatever it might be, it should come back and say, no, that's actually false. That output doesn't match with the proof that was created. Yeah, so we get false on that because that's not actually the value that was produced from this particular proof. So this is obviously a very, very basic example, this particular circuit using this .circom language. But that's essentially like at the end of the day, that's all you really have to know. For at least the kind of proofs that I'm trying to generate is know your rules, generate a verification key for it so that the proof that's generated has this guarantee that the rules were followed. This obviously gets really difficult, or at least it gets really involved in my case of trying to prove the game Pong, because doing this zero knowledge verification is quite expensive. And it's not expensive on the fee side of things, right? It's just the Sorobon side. The only thing it's doing is just is validating the proof against the verification key. But building this proof can be very, very expensive. In our case, the only thing we're proving is A times B, and produces this output of C. In the case of Pong, you're doing complex physics math, and you're doing that over many, many frames. Like a game of Pong can last quite a long time, which means there are many paddle movement events, there are many scoring events, there are many ball interact with paddle events, there are many wall bounce events, there are probably checkpoint events to make sure things all look good. And so you're doing two things, I guess, in my case. The first is when you've got multiple events like this, trying to generate like one Groth 16 BLS12381 proof over this just wouldn't work. It would take ages to verify, to like wrap up all of it. Would require a tremendous amount of compute power and memory just to hold the entire sequence of events and wrap it into some sort of proof at the end of the day. It would be a huge verification key. It would be, this, I don't know how big. Let me look at how big this actual verification key is. Does it have, it has the Z key here. The verification key is actually not that big, but the program itself, when it gets compiled, can often be quite large. And I think that comes into play maybe in this key here. I can't remember. But some of these things can get to be very, very large when they actually generate keys. Yeah, that one's not the big one. When they actually run, it has to pull all these things into memory and actually run all of the verifiers and produce the proof. And the more arguments you add, the more outputs you add, the more events that you add, the bigger and bigger and bigger it gets. And that's where you come to this concept of folding, where you've got like zero knowledge folding, where it takes events and slowly like wraps events into events and just creates this chain of events that are all proved iteratively, but it's essentially prove iteratively. Prove that this frame or this event is valid. Cool, it is. Make a proof of it, and then pull it into the next one. Include as one of the arguments of this next proof the last proof, and then prove it again with the same physics for whatever event it was, and you just kind of keep doing this iteratively over every event that comes in. And then at the end of the day, after you've folded all of these events in, you then produce one final Groth 16 BLS 12381 proof that you then actually have this nice compact. It'll be the same size as this. It's just proving different arguments and will have different outputs. It'll still, I guess in my case, be did player 1 or player 2 win? And then that's what actually gets proven on chain. But how you arrived at that final proof includes this concept of folding proofs together. But that is a different type of cryptography. There are different libraries and different cryptography that does this folding. And so now you've got, instead of using Groth 16, you're using some other proving library, some other proving system to build that, with the final output being this Groth 16 BLS 12381. So keep that in mind. Again, if you're building out a big events chain, you're going to need a different type of circuit, probably a whole different library for doing folding. There are specific programs. There's like one called Nova or Hypernova or something like that for doing folding specifically. There's this program that I'm really excited about called RISC-0, which does this folding logic, but they don't have a Groth 16 BLS 12381 curve yet. They've got a BN 251, but allegedly we'll get that curve very soon, and probably the next, or I guess not the next, but the next Protocol 24. So then this RISC-0, I've had a ton of fun. This one's very, very fast. It's very specific to being high performance. It's written in Rust. Building out, instead of building SIRCOM circuits, you can write your circuits in Rust. You can use the same prover logic. What's kind of nice about that is you can actually use the same physics engine in your circuit that you do in your actual like game engine. Particularly if you're using something like the WebSocket, you can check all of the WebSocket events directly against the Rust game engine that you're using in your circuit that you're also using in the WebSocket to verify those events, which is quite cool. I have a version of Pong that I built using RISC-Z or RISC-0, but because it spits out the wrong proof at the end of the day, I can't actually. I guess I think we have an example. Actually, it just doesn't use the host environment. Oops, wrong one. Stellar. It uses the guest to do the BN254, which is going to be incredibly expensive. I don't even think this would work on mainnet to prove this, but I don't know that for a fact. So I might actually go back and try and use this example to do a proof of one of these RISC-0. This one was it's very fast, and for this like roll-up type of stuff. They're using this for actual like just a lot of very almost real-time zero knowledge proving, specifically for stuff like games or bridges. Pretty cool. Yeah, right, Rust, not circuits. So definitely want to check this one out for how to actually get proofs generated. It's awesome. Okay, so that's kind of like at the end of the day, there's not a whole lot of additional things to say. I would say you've got the repo. Actually, there's two repos. I just pushed another one. If I go to, what was this called? Groth 16. Yeah, right here, Groth 16 verifier. I've got this library that's the website actual Sorbonne prover that I'm using just for that really basic circuit example. So you've got that one, but then you've also got one I just pushed, which gets almost all the way there, other than it's not spitting out the right proof. It's spitting out the BN254 proof, but you've got this one for understanding how RISC-0 works. And when I say works, like massive caveat for both of these things is they were 100% AI coded. So I take no responsibility whatsoever for saying anything in them is correct. I do know what it should do. I have no idea if it's actually doing that. Like when you actually write some of these things, particularly if you try and one-shot zero knowledge proof games, you will find that the comments for these things are absolutely riddled with comments like in a production environment or in practice, this like idea of we definitely didn't do what you asked, but if you wanted me to, this is how it would be done. So don't get too far down your excitement route of this thing's actually working until you've done an audit of all of the code for comments like this is a mock, this isn't real. In a real production environment, you would actually want to. I've got like 1, 2, 3, 4. I've got 8 repos right now where I've tried to do this in different forms as I've learned, you actually need to do folding because that was going to take 45 minutes to verify 3 moves in Pong. Okay, they've got this concept of folding. Let me start a whole new repo and try to do folding. Oh, shoot, it's using the wrong curve. Let me try again with the right curve. Once you start heading down the wrong path with some of these things, it's very hard to get AI to understand what you actually meant, and trying to retrofit and go back and erase bad code or unhelpful code and try, switch curves. It just won't do it. So you have to kind of start over with what you know now. What was I going to say about that? I've had to write so many of these repos, and I remember one of them, I found one line, because I had very explicitly told it, do not write mock, fake, testnet code. Like, I actually want this to be secure. I'm trying to write a zero-knowledge game that's unhackable. And it was like, cool, got it. Definitely going to do that. And then looked through the comments and found 20 places where it was stubbing in or just entirely bypassing. I think it wasn't even doing any proving at all. And I was like, this thing's so fast. That's incredible. Only to find that it wasn't actually running a prover at all. It wasn't running my circuit at all. It wasn't verifying the physics logic at all. And when I switched it over to doing that, it was taking much, much longer. So keep that in mind as you use AI to build these things. I have found AI to be very good, particularly if you're using MCP servers. If you have if you help it to know what libraries you want it to use, I have found that having a long conversation with ChatGPT first to hey, here's what I'm trying to do, ChatGPT. What are some of my options? And then you can evaluate some of those options, which will give you libraries that you may want to use over others. And it just helps you reason about your project, particularly when you have no idea what you actually want, to start asking AI what your options are, but not in the format of it needs to try and code something yet, because it'll probably get it wrong. It'll just make too many assumptions. To have a long conversation with ChatGPT to try and get there. That's how I found out about this thing called IVC, which is the idea of folding. I don't even know what IVC stands for. It's iterative verification computation. I don't know. I just completely made that up on the spot. Sounds amazing though. I could be good at naming crypto stuff. Let me see if any of these have. This one wouldn't. Let me pull in my other IVC test and see if it tells us. I bet it probably does, particularly if I look up the capital IVC prover, incremental verifiable computation. I was actually very close. That's amazing. IVC folding is also referenced here for some reason. Incremental verification of event sequences. I had no idea what it was called or what it was, but through having a conversation with ChatGPT way before I asked any coding model to one-shot anything, I educated myself so that I could say, use Groth 16 over this particular curve. You're going to need to use IVC folding and use this particular library to do that, and avoid doing this because I eventually want to have the verification key put as output as a JSON file, and I want it to follow this particular format. And I would paste in. I do this all of the time now when I'm asking AI to code anything. Is I just paste in the repos that I wanted to use as examples. So I would say review the Groth 16 verify. I would actually copy this URL. I would literally go in and say, hey, I'm going to copy this URL. Please use those JSON files as the template for how I want you to output the proof and the verification key and the public values that you output. Follow the examples, like giving it as much context as it possibly can so that it A, knows what it's trying to do as an output. It doesn't start to guess, but B, it also knows the context of the environment that you're in, that you want to use Rust, that you want to output Sorbonne related stuff, or I often will tell it to start by writing a Vite React Tailwind front end or something like that. But providing it Git repos or links to articles that are public, just providing it loads and loads of context so that it's not trying to guess. The other thing to keep in mind is, and I've mentioned this before with the AIs, I think still most of the data is from 2024 and tons of ZK stuff has happened in 2025. So you're going to have to work very hard to remind it to pull information that's more recent. If you can find articles that like people have written or tweets that have been posted in 2025 to use as reference material so it updates its knowledge base, it'll help you a lot, because 2024 was when some of this stuff was just getting started. 2025 is really where ZK stuff has hit mainstream, and so tons of work has been going on. Loads of features have been added, and you don't want to be using old versions of stuff. And just generally, LLMs don't know how far ZK stuff has come. You're going to have to provide it more information to ensure it's actually using all of the new latest and greatest features that have come out in the last 8 months. All right. So obviously that's not like, I'm still working on the Pong stuff. It's a real battle between making sure the WebSocket system is actually working, making sure it doesn't prove the wrong things, that the IVC is actually working, the folding is actually working. Stay tuned. But I would love for more people to get involved. Maybe don't pick a physics-based game like card games, checkers, things that don't involve physics and more involve just basic follow these rules. Chess, I don't know. There's a lot of games. Any card game basically doesn't involve physics. That'll be a lot easier to prove and build verifiers for. AI will have a much easier go of that, and it'll just be faster to prove. My games are taking like minutes to get the proof for, because there's so many events to roll up and prove. Hopefully when we get the BN254 or whatever it is prover and we can use RISC-0, it'll be a little faster. But big takeaway, don't be intimidated. AI can help you with all of these things. It's so much fun to build things that you have no idea how they work or why they work, and to just learn. Let AI teach you. I've just had a load of fun with it. And yeah, if you build a game and we'll actually maybe get it live on this blend together contract, and people can play it and win points for their faction and make real money, because we're in this crazy world of DeFi, and I'm just so excited to tie these things together and see what's possible. All right, any questions that people have? I'll scroll back through. I was kind of keeping my eye, and I don't think, in my opinion, Pong doesn't really make sense with ZK. You can sit down, sir. That's why I'm doing it. The proof takes too much time to generate. It does. It's not good. Zero knowledge stuff is really bad for real time, which is why I'm really excited for the RISC-0 stuff, because that's kind of what they're aiming for. Is a little bit more of the real time stuff. Battleship is a great example. I also think Battleship is stupid because there's very little skill involved. It's kind of just click and point. I like games that include a little bit more skill. So that's what I'm trying. I also, it does, Pong is a stupid thing to try and zero knowledge proof, but at the same time, if I can do it, it opens up so many opportunities for some of these simple physics games like Asteroids and all these retro games that I love that do involve a bit more physics. And if Risk Zero can help us in that regard, that would be amazing. Bingo. Yep. Again, if we can find a skill-based game that doesn't have physics, that would be awesome. And I think there are some of these. And some of those are like, okay, the skill is more psychological. Battleship, I feel like there are people that are probably better at Battleship than others. But I also think you get two people together that are mediocre, that are pretty good, and it's kind of like tic-tac-toe. Is tic-tac-toe a skill-based game? You get anybody that's like decent at it, and you're always going to tie. It's kind of like that. No, okay, well, we'll do 3D tic-tac-toe. All right, fair enough, but then nobody's going to want to play because it's impossible to grapple. Anonymous voting. Stella does hallucinate pretty badly. But if you provide modern, ChatGPT or anything with an MCP server, coding models provided with context, I'm finding it does an amazing job. Again, I was able to build this, which actually does zero knowledge stuff entirely with AI. I'm definitely one-shotting or getting pretty close to one-shotting entire Stellar applications, contracts, front-end code, wallet connectors, without having to write any of the code by hand. And some of it's because the LLMs are getting way better. Some of it's just because I'm getting way better at understanding how to provide appropriate context by referencing repos that do what I want it to do or follow the patterns that I want it to follow, versus hoping that it has the right context by default. Most LLMs really don't. You kind of got to think of like LLM more like a kitchen, like a gourmet, or what do they call those? Gourmet kitchen? What are those called? Commercial kitchens? I don't know. But you still have to provide like all of the appropriate ingredients and even additional like tools and machines so that it can really make an amazing meal. It's a combination of LLMs and the context and just your own skill of informing your chefs what it is you want them to make and the ingredients. I don't know, the analogy is getting weird. All right, fantastic. Well, I look forward to seeing what people build. The zero knowledge stuff is super, super fun. And it's just a wild superpower of being able to say, I could write a program that I could give to some random other person, maybe even someone I really don't trust, and the server, the players, they have to follow my rules in how they run this game or use this game, and not have to do all of that on chain, but to do it in this like off-chain environment through the proving. And the proof I get at the end of the day, if they say they won and I really don't trust them, it doesn't, like, it's fine. They had to follow my rules. They had to follow the rules engine. And so I can be guaranteed that it's safe to give them their prize money, even though I have no idea what client it was run on, no idea what server ran it. I really don't care because they had my verification key, my public key, my verification key, and they had the program that they had to follow, the rules engine, the circuit that they had to follow. So cool. I'm worried that with this ZK AI, we're going to do some vibe thing, which is going to handle money and not be secure. 100%. That's definitely going to happen, which is why don't run your own money stores yourself. Don't do a lot of transfer stuff. In this particular case, I'm borrowing Blend, and I'm borrowing SoraSwap, and I'm borrowing the Fee Vault. Anytime money's being handled, it's not being handled from a contract code that I wrote. It's being handled by contract code that a human wrote that was audited. I have a much higher level of confidence in that. I'm just tying into those things. And in that case, yeah, my game may break, but at least nobody lost money. That's the idea anyway. You do want to make sure that is, particularly again, as we work on these things. I don't know, there's a really cool concept of just like the composability of the amazing things that other people have built that is audited. How can we grab a hold of those things and use them in like more dangerous, fun ways that are safe because all of the dangerous pieces I didn't write. And then, yeah, some of it's like, let's just use it, run with it, and then make it an upgradable contract. And for the next like 2 or 3 years, particularly because there's the honeypot of if you hack this, you could earn all the yield. Can't steal anybody's money, but you could earn all the yield, I think is a really cool honeypot to say, hack the crap out of this. And then we'll just begin to patch it as people steal yield until we have a system where stealing is much, much more difficult or just straight up impossible. Because the contract's always upgradable and all of the deposits are handled by a completely separate contract. Okay, there is one more thing that I was supposed to mention, and I must mention it because who knows what will happen if I don't. And that is that there's a workshop, a Hack Meridian. For those that are going to Meridian, there's a hackathon. Definitely need to attend that. It's going to be so much fun. I'm going to be there. Elliot's going to be there. The whole team's going to be there. I'm planning on, I'm not going to be a student. I'm taking all the money. That's not going to happen. Hack Meridian is coming up. There's a workshop happening in 4 hours. Please go and attend that. It's going to be the cheat sheet for how to bring home the dub at Hack Meridian. I believe some Blend guys, the Blend, somebody's going to talk about is apparently about Blend. So I'm going to be there. You're going to be there. You're going to click that link. You're going to subscribe. You're going to watch it. It's going to be awesome. And then when you win, maybe you'll split some with me as the 5th member of your team. And Elliot too, right? Okay, fantastic. Well, go watch that when that goes live here in a few hours. Otherwise, have a fantastic rest of your week. Let me know what ZK things you build, and I will catch you later.